Okay.
Yeah.
So welcome everyone to the webinar number 5 of a series of sessions hosted by the European project Presence XR. So this session is going to be recorded, and please use the Q&A for your questions, or raise your hand at any time, or raise your hand at the end of the session if you want to make the questions yourself. So I'm delighted to welcome here today Sergi Fernandez Langa, who is the CEO of Volume Technologies and the Director of Research Group Media Tech at I2CAT. Sergi's background is defined by a decade of leadership at the intersection of academic research and market innovation. So for 12 years, he served as the Director of the Media Tech Research Group at the I2CAT Foundation. Under his direction, the group established a very strong scientific reputation, producing extensive academic literature and driving a clear technological evolution through major tech transfer deals. During his tenure, he guided his teams through the complete transformation of the media landscape. The research he conducted provided the foundational technology for several successful startups. One, iGlor, which is an I2CAT first spin-off in the audiovisual sector, which now creates multi-sensory experiences for world-class artists. Watch Chitty, which focuses on agile audiovisual production for communication and marketing. And Into Reality, dedicated to synchronized multi-camera production for sports and cultural events. Building on this extensive experience in fostering innovation, he has now taken the helm of building another startup, which is Volume Technology, and he's the CEO. His current mission is to push the boundaries of interaction, remote presence, and our understanding of the world through advanced volumetric video technology. So I'm delighted to welcome Sergi on this webinar and to listen to all the insights on how he has built this technology. So thank you, Sergi. The floor is all yours.
Thank you. Thank you, Veronica, for your kind introduction. Let me share screen. Let's see if this works well. You should be watching my screen now. Are you?
Yes, you can go on.
I don't see you. No, let me just see.
Oh, I'm going to take my camera so the floor is all yours and everyone can just listen to you.
Okay. Anyway, if anyone wants to interrupt, please do it. Yeah, I'm here to talk today about the future, but also about the past. So I want to show you what we have been doing and what we have in our hands today. As Veronica said, I'm leading the Media Tech department in I2CAT, and I'm also the CEO of Volume Technologies. I will be having this double role during the next 6 months. So here I'm going to present a little bit everything we're working on. But Volume is about real-time communications, real-time volumetric video communications, right? And this is basically what we want to achieve. We want that humans that are at distance, they communicate together, and they have the feeling, they get the feeling of being really together in the same space, being this space, a physical one, my physical one, your physical one, or a shared space, virtual or physical. And that's what we are trying to achieve in Volume and also in I2CAT.
Sergi?
And yeah?
Is Maria here? It is possible you hide the bar, the below bar?
That one?
Yes, for the recording.
No, it's not possible.
You have 2 screens, isn't it?
Yeah, I have 2 screens.
You can move this to the other one. Don't close the bar, but just move.
Okay. Oh, okay. Okay. There you go. There you go. Now it looks better for the recording. Yeah, thank you, Maria.
Fantastic. Thank you.
So basically, in this picture, in this image, what you can see is Apple's proposal on, let's say, holographic video conferencing or volumetric video conferencing or social XR, social VR platforms. That's the proposal. And to be honest, I think that we can go much, much far than this. And there are multiple problems to do it. The first problem, of course, is to have the headset on your face, but there are many technical problems to have the true volume or volumetric representation of that person sent and rendered in the other side. This is what we are doing, and this is the status of our technology today. One of these two people is not there. Obviously, it's that one, Mohammed. He's not there, but you can see that the level of realism starts to be really good. This has been captured just with one depth camera. Okay, of course, they don't see each other. To see each other, they would need some VR headset. But we assume that this is going to evolve somehow fast. So we expect that in the next 5 to 10 years, we are going to have really thin glasses. Of course, the market, let's say this is not ready for mass market, basically because of the need of that type of headsets, right? But there are many other things that we can do already today. I'll get into detail. I'll try to launch this video, and I just want you to see it because for me it really represents what we have been trying to achieve the last decade. And it was very nice to see some years ago Microsoft doing this video. And it has also been sad to see that somehow Microsoft is hiding this technology and they don't advertise this video anymore. And probably they have their own reasons for that. And yeah, we can discuss about that after this session. So just let me show you.
Yo que tengo mascotas, ¿cómo puedo proteger mi casa? Con la alarma de Securitas Direct conectada a policía. Porque la puedes activar cuando
That's the video. Enjoy.
Connection is a spark that gives our lives meaning. It drives us to seek out others who feel the same way.
Okay, why don't you input the data and we'll take a look together. Hey Mari, what you got for me?
To find those who share our views, yet offer different perspectives.
So this net. Look over here.
Challenge us with new ways of seeing.
That I think we should
Deepen our understanding. And enrich our lives.
最后一笔是收入，往前。
Great things happen when we commit to something bigger than ourselves.
Take a closer look at it.
place this here. Let's see how we go from there, okay?
This sense of collaboration and the feelings of connection it brings excites us.
Hey, just in time. I'm gonna move it slightly, okay?
It's yours, take it.
We have 2 planes right now on the same trajectory.
As we put people first, technology fades into the background and feels like anything but.
Aisha, what do you think?
I think if we had 330, maintaining 2800, we'll be clear for approach.
Excellent.
This changes the way we see the world, and in turn, changes the world we see.
These numbers are looking great, actually.
There's promise in the possibilities, and what we see and create next will stretch the imagination.
Good morning, Sarah.
Morning.
Slowly coming towards the thumb.
A world without boundaries.
Good job. A lot better than yesterday.
Yeah.
Excellent. Slowly bring the
A world where technology enhances, not limits, humanity. With people front, center, and in the spotlight. The future is here. And here can be anywhere. Introducing Microsoft Mesh.
That's it. Let's see if I can go back to the presentation. There you go. So basically, in that video, we have seen the proposal of Microsoft towards social VR or holoconferencing, or how they call it, and patented, by the way, holoportation. The technology is getting to a level in which very soon we're going to be able to reduce the physical limits of connection of humans across the globe, and that's wonderful. And we are on that, basically. We are working in every single piece of the pipeline that is needed to generate experiences better than this one, right? That was made in 2019, I think, or 2018. And this is also what we are trying to do in the Presence project, right? We developed volumetric video pipelines real time, and in Presence, the Presence project, what we are trying is to improve the feeling of presence that a group of humans have when interacting together into an XR environment. And I say XR because it may be, a pass-through application or a fully VR application. And so the last 12 years, I've been the director of the Media Tech Research Group and I2CAT. And basically, in the group, what we do is network immersive and interactive video technologies. And we apply them to create and to explore new type of media experiences. This includes volumetric video reconstruction in real time, AI-based volumetric reconstruction, real-time compression, transmission, and rendering, and also scalability, and also platform integration, how we offer all these features together in one social media platform to communicate humans at distance. And by far, the most difficult effect that you can create is the feeling of presence. To make someone feel that is really present in an environment that is not, let's say, the reality, or what we know as reality. And that's precisely what we are trying to address. Why? Because as we progress, the use of tools like video conferencing gets more intensive. We use it more. In parallel, we are less together in the office, let's say, or in our place of work. We are more working or interacting with others in general from home. And this grid of 2D videos, we consider that is not enough to generate true connection and to generate deep collaboration at distance. Basically, we want to go from here, that's what we have today, not to here, that's the social media platforms that you can see around, and something more like this. And I will show you a video of this later, okay, in the right context. But this is how it looks today. This is basically a pass-through capture, a capture from the video that is a capture of the video that you can see from your VR headset, right? So that's the impression. When you look at this scenario, that's what you see, two people sitting and talking to each other. Of course, one of them is not there. Same thing, we are able already to, with Gaussian splatting, create, capture, and render ultra high realistic environments, static environments. For dynamic environments, still a bit difficult, and there's a lot of work in that domain. And we can embed that type of, we call them volumes, human representations in these environments. This is a video that we recorded more than 1 year ago. You still see issues here and there, but I'll get into the details later. So in a nutshell, what we do, we are building analog conferencing platform. We put cameras around the user. We capture the user's body from different angles with depth, and we compose a single geometry of that person. And then we are able to compress the geometry, send it through the network, and render it in the other side. And today we are offering an SDK that facilitates this work for everyone, right? Specifically to Unity 3D developers. That includes all the different software components and models that you need to make that type of experience possible. And of course, when they ask me, okay, but what's the use case for that type of technology? I always answer, what's the use case for video conferencing? Right? So there is no one use case for video conferencing. Video conferencing is a tool. Then holoconferencing will be pretty much the same. It will be a tool that can be used in multiple scenarios. For instance, simple holo call. Instead of a video call, a holo call. We will be able to call another person and see that person in volume in front of us and interact with our whole body naturally, without the limits that the 2D screen and the 2D video camera impose. Meetings, same thing. First, we want to talk one-to-one, then we want to talk in meetings or in events or to support marketing. So instead of sending people somewhere to present something, you just have some equipment and your company members, they're there virtually. You don't have to waste CO2, spend 1,000 hours in a plane, in hotels and so on. So this is going to optimize a lot let's say the human transport in our planet. Then we will be able to connect offices, buildings, and they will be equipped in a way that the integration between the digital and the virtual is going to be seamless. And more use cases, right? Heritage, remote training, or care. And this is the last use case I think I have. But this one is very relevant to me because we are in discussions with Vall d'Hebron Hospital here in Barcelona, one of the most important public hospitals in the country. And I was discussing with them some months ago. I was talking to the pediatric oncology, the director of the pediatric oncology floor. And he told me his expertise is leukemia. And he told me that his patients, in the end, they are kids. They go, from 0 to 18, but let's say they're young people. They go through long term procedures, and some of them spend in the hospital 6 months. And during all this time they have given to the disease they are suffering, they are completely isolated. They can only interact normally with one person during the whole process, during the whole 4, 6, 8 months, with one person physically. And normally this person tends to be the mom. Yeah, right. But besides the mom, the mom, that of course is the first one he or she is going to call in some event. The kid is going to lose contact with brothers, sisters, with father, other family members, and also with friends from the school. So already today, our technology can serve very specific purposes where even with the quality that we can provide today, you have seen more or less the quality, right? There is still a lot of things to not many, but a lot of things, so some things to improve. But these use cases already introduce value, already provide another value today, right? Even if VR is not ready for mass market. We are very aware VR ready is not for mass market, but in very specific use cases, XR, VR, holoconferencing, volumetric video communications are ready to solve things today. And this is, I try to recreate how this experience could look like for a kid. Right? Imagine this is Mohammed. This is not a kid, but Mohammed is sitting, laying in a bed, and his friend comes and visit him, and they can have a realistic interaction. Right? Of course, we did this environment more for kids because we are trying this in a pain relief scenario for kids. But that would be how father, brothers, sisters, and the patient would see each other. And believe me, when you try it, you really have the feeling of being together. And if you use the pass-through mode, even more. So that's a thing. Of course, first thing we did is to be able to capture a body, compress that volume, and send it through the network and rendering in the other side. So we could have one-to-one calls. But the next thing you want to do is to meet with more people. And that's what we started to work like 3-4 years ago. That's a video, the very old video. The reconstruction here is only made with one camera. But you can see we have 6 users at the same time. Of course, they don't have a headset, right? So they cannot see each other. But as soon as they get the headset on, they are in the meeting room and they can see each other, right? That's what scalability means.
I can
to
see you
us.
too. I can see you here in
I think
in
we
the
use the
other
audio. Let me see if I can get you. Of course, the camera. Let's say there.
at the office of AutoCAD. You too. I can see.
You see, this representation is very like the one we saw in the Microsoft Mesh video, right? The transmission basically and the data format that we are using probably is the same that Microsoft Mesh was using by that time. And we are improving it. You will see in the next slides. And of course, the problem here is that you only have one camera in front of you. So for the, let's say, the central part of your body, the boxes are together because the camera sees them very well, both the color sensor and the depth sensor. But as you get away from the, let's say, the sweet spot of the camera, you see some separations here. And of course, because the depth is captured at a regular range, the interval of, I don't know how to say in English, right? So when you go in this corner, it's more difficult. So this is why you see this light. But the feeling that these two users are having is that they are really together. And that's what really matters to us. And here another example.
Trabajar con otro tipo de modelos 3D que nos permitan mejorar la calidad.
This is a company. Wait, this is a 2D video billboard. This is made by Brainstorm. Brainstorm is a company working in the virtual production domain. And what they do, they have a camera, they have the presenter, a green chroma key behind the presenter. And since they know how the camera moves, they can render the background, right? And they just generate the feeling that you get the perception that they are capturing this person in volume. They are not generating the person in volume. What they are doing is tricking our eye by changing the background, right? But of course, for them, it's very interesting what we are doing because now they have to sell, let's say, one camera and one with their sensors and one render per view. With our technology, they can have as many cameras as possible. Not only this very expensive solution for broadcasters. When you want to introduce that type of features to, let's say, less high-cost productions, you need to reduce costs. That's what we are trying. Instead, this person, for instance, has been captured with our technology. Of course, the quality is not the same. Right, you can see the difference, but it's not that far. It's not that far. We are getting closer and closer to being able to let's say, achieve the quality that we have today in the broadcasting. This is another example, for instance.
Calibration board in your camera setup. The magic happens automatically as the software detects known reference point on the board, allowing us to instantly align your cameras to each other with no.
Still, again, this has been captured only with one frontal camera, depth camera. But these are, let's say, that's a capture with it. That was Qualcomm, so probably that was 6 months ago, maybe a bit more. But we're slowly improving the quality of the capture. Right? I'll get into details. So, to do this, to offer, let's say, the ultimate holoconferencing solution, there are many problems that we have to solve. The first one is capturing the data, right? So when we speak about volumetric capture studios, that's the image that you it comes to your head probably. So a lot of money. I see these. I only see euros everywhere. It's the LEDs, the metallic structures, the cameras, reflectors, the painting, the space. Very expensive. Very expensive. And these type of captures are really very expensive. Only possible for high-end production. Us, or let's say the research community, we are not probably able to get to that level of productions, and also it's not our objective. In the end, we want this technology to be very easy, very affordable, and we want this to reach everyone in the planet. So we cannot go with high-end deployments. That's not a high-end deployment, but this has also some costs. I wanted to make a picture of my lab. This video our lab today, not you. So that's my lab, and you can see how it looks like, right? A lot of cables, a lot of cameras, a bit messy in the end. So not ready for a production. So this is a problem that we find every time that we go somewhere and we want to deploy one of our recordings or streamings. There's a complexity on the deployment. So one of the problems that we are trying to solve is how to make this easier and cheaper. If you see here, you have this huge PC with two or three GPUs to process all the data from these cameras. I'll get into these cameras later. But we want to eliminate this. We want to do this in the edge, right? But at some point, we are going to need to process the data on premise. So right now, we are developing pipelines to split the processing that we need to do on cameras on the, let's say, edge closest to the camera. That would be an embedded hardware like this. That could be a Jetson Nano, or not a Raspberry Pi because we need CPU by the moment, but anything that can compress color and depth video, color and depth textures in real time, right? So you don't need to do the whole processing in your closest server. And once you have compressed this data, you can send it to any server in the world and do your processing there. So basically, that's what we are trying to do today. So this means that to integrate the synchronization of multiple cameras, to split the compression effort and get it close to the cameras, and to transmit every cameras independently to an edge processing machine with GPU capabilities. But still, these type of setups, very complex, very messy. So what we are doing today is to embed all this technology in very, very simple objects that you can just send, build, and all the cables are in their place, and you are not going to have issues with the end user. Why? Because what we have seen is that sometimes XR or VR still seeing something, is a niche, and still is very difficult to deploy experiences with high-end computing and peripheral, let's say, requirements. So with these devices, these are an holototem. This simply captures your body from central view, and you can call another person. This is basically a table. If you press here in the black thing, some cameras get out, and let's say if you have two tables, two users in one table, two users in the other, they will have the feeling that they are together around the same table, like imagine for offices and so on. And if you want to go to a higher level of quality, to a higher level of reconstruction, full body with 7 or more cameras, you need something, let's say, more serious, like this. But the next step is a volumetric video studio, and is super expensive. Now I'm going to get into the reconstruction itself. I want to show you a video of the VR Together project. That's a project we executed from 2017 to 2021. And I want you to see the quality of the reconstructions we had by that time. Okay. Let's see, we have
The VR Together application is compatible with the most popular immersive media content, spatial audio, and both 2D and 3D video. In VR Together, you will be fully immersed in the virtual world. The real-time volumetric video will project you in the scenario. Together.
Okay. I think that was the VR. I don't know if there's anyone in the audience from the VR Together project. That was a very relevant project, because a lot of technical and scientific progress was made here, and many of the things that we are implementing today, they were born by that time. But please see the reconstructions. That's the quality we had 4, 5, 6 years ago. And now if I can get out here. No.
With your friend.
There you go. So that was the quality we had, like, let's say 5 years ago. Let's see how it looks today. This is how it looks today, but wait. This is basically the same technology we had with some calibration process. What we are doing is calibrating the multiple. In this case, we have 7 cameras, 6 cameras. Yeah, 6 cameras around this person. And what we are doing is calibrating these cameras and generating one point cloud per camera and putting all these point clouds together. And that's the result that you get, when you use the plane output, the plane data from the camera and the different cameras, and you align these data. Okay. So the result is pretty bad. Right? You have in the stitching, you have problems in the stitching, you have problems in the hands, you have problems basically in every detail part with occlusions and so on. So this is what we are trying to solve right now. Let's see if I can go to the next. But if you apply some smart filters, you get things already like this. You see, the stitching has disappeared. Of course, you still have issues, but that's actually pretty amazing. Can we on the back of this person and the quality? And that's, let's say, volumetric, so you can go around the person, right? So let's say that the shape, the geometry starts to get better and better. And of course, you still have problems. You have problems here, you have problems here. The silhouette detection, so it goes, it improves slowly, right? And I want to show you another. Maybe this one looks a bit better. So of course, you still see issues here in the hands, but that's the most complex part. And you see the resolution. The resolution is low, right, in the face. But this is not a complex thing to solve. That's having a better camera, higher resolution on the frontal camera. And this is why I want to go back to this image, because precisely that's what we are going to do in the present project in the next few months. In this project, we have a partner, it's called Greatrix, and they have these super nice cameras. These nice cameras are light field cameras and high resolution light field cameras. This means that we can get a very high resolution texture of color, and we can get a very high resolution texture of depth with an accuracy of the depth that is higher than the accuracy that the time of flight technology is giving to us today. Problem: you need some milliseconds to process this data to get the right depth. So it depends on the time that you have. Once you have a reconstruction, once you have the geometry of the human body, you want to send it to the other side. You want to send it through the internet, right? And there are different ways to do it. In our department, we are exploring. Basically, we started using a point cloud codec, a geometry-based point cloud codec. This is the one offered by MPEG, and it was the anchor used in the first MPEG volumetric video test, volumetric video compression tests dated in 2016. So we were using that codec, and that codec had a upper limit of 30,000 points per frame at 15 frames per second, if I'm not wrong. So the last 3 years, we have developed our own point cloud codec that works real time, and we have it in different flavors. Why in different flavors? Basically, because what we do is a projection of geometric data into the color space, and we use regular video codec to send this color texture. But when they say H.264 is lossless, that's false. It's not lossless. It's lossless to the visual human capacity. But if you really do the whole compression, you see that you have lost data in that process. And that's, for the color, this is okay, because your eye is not going to appreciate if the red is like the super red or the super red. But in this case, when you are transmitting geometry, losing data impacts on the visual quality, because the point that you are trying to compress and send to the other side shouldn't be moving. It should be a static point, let's say a static every frame. But when you transmit it and introduce some noise, the point moves like this. So the whole result of the volume is like a sandy thing, right? So we implemented a lossy version with H.264 and H.265. We tried different projections. We tried to duplicate data somehow and send the data through different compression pipelines and gather the whole data on the destination. But anything of that worked, and when it worked, the bandwidth was huge. So we opted for working and implementing a really lossless compression method based in static image compression methods. And that's somehow the status today. We are able to change the compression of our streams. We are able to send and stream every human representation to the server or to the other side. And depending on the network, depending on the reception or transmission capabilities, we can tune up and down this compression. And of course, this is going to result in more or less, let's say, aberrations, you can call it, of your original data, right? So that's the original data. You see here the depth data, and you see the impact of the compression pipeline depending on the model used. That's a PSNR compression, basically just to show you that more or less they are all together in the upper part of the table, but of course BPCC, that's the current volumetric video-based point cloud compression system, behaves better than ours, let's say, but there's only one inconvenience: it doesn't go real time. our compression methods for volumetric video, they work real time. Of course, we go real time, so we cannot deliver the same data. We cannot introduce less errors in the data, right? Because basically we go real time. This is how it looks. A single camera capture, uncompressed. Let's say that's the pure data. That's what you get. In this video, you can see a comparison of the different compression methods that we are using today, being it lossless or video-based, let's say lossless image compression-based, lossy video compression-based, and using both H.264 and H.265. So as you can see, of course, the lossless compression pipeline works better, right? That's, you send all the data to the other side, so you're not going to lose any data. But if you are in some situations where your bandwidth is restricted, you can use video-based compression, and you can adapt to the compression rate, and you can adapt to the bandwidth that you have. So let's say with CRF17 is already compressing a lot. Yeah, the difference are not that high. Yeah? The difference are not that high. And of course, you have to think that we have been working in 2D video compression methods, codecs, for 30 years. And we have been working in volumetric video compression codecs only for 10. So we still have 20 years. Well, that could be one way to look at it, right? Once you're able to compress your data, you want to distribute your data. You want to send it to others. You want to send it to the server and do stuff in the server, or you want it to your representation. You want it to reach and be seen by somebody else, right? And this somebody else can be one person or multiple persons, right? As I was saying, first you want to transmit to one person. Once you get this, you want to transmit to multiple persons, and then you also want to see them. That's natural, right? Like in video conferencing. If you remember, we started just with 2D video streaming one way, and then video conferencing two ways, and then multi-user video conferencing with many users. But it was not until 2020 that we got used to these events with hundreds of participants, right? And if you remember, in the pandemic, video conferencing systems were not ready, were not built to serve hundreds of users at the same time, right? And this was the reason why Zoom impacted the market that hard in a sector like video conferencing that was somehow solved, right? So distribution is very. What means distribution, or what we want to achieve in the distribution section of our work? In the end, as I was saying, we want to increase the number of clients per session without relevant impact on the quality of experience. Then we want to optimize the system when there are multiple sessions happening at the same time, right? First, you want to serve one session, but then you want with the same server to serve many sessions, right? See, different optimizations need to be in place with that. And finally, you want, if you're able to interact with the cloud and infrastructure provider and get the best service possible from their infrastructure. And to do that, you can do it with humans. Let's say you have a DevOps, you have people that interact with the service providers, networks, or cloud, and fine-tunes your systems to perfectly. Or, as we are observing lately with the 5G and 6G initiatives, is that your system can talk directly to their system. You can prioritize the streams, prioritize certain tasks, deploy services on the fly, and so on. So this is also something we have been exploring very recently. Very recently means the last 2-3 years. So let's see that we start with a system that has, let's say, the typical configuration, right? This is server-side architecture, server-client architecture. So you have a monolithic thing in the client, monolithic thing in the server, and it works. And that's it. That's your first approach because you want to show. And we can do many things in our way to optimizing communications. We can do many things. And especially now that apparently we are going to be able to use processing in the edge provided by, let's say, us because we have the edge, or provided by some operator. This is happening. The business model is still not clear. There's, let's say, big corporation fights there, but it looks like we are going in this direction. So in our original architecture, we identify different components that not necessarily need to be deployed on client or on server. They can be deployed somewhere in the middle. And that's what we are exploring. I want to show you the first, that's a video of a multi-user holoconference with a server-side component that is called PCMCU, Point Cloud Multipoint Control Unit, that what it does is control where the user is looking at and just trying to send the right data, right? So if I'm watching someone, like in this case, I have this person in the middle. I want this person to be in the highest quality possible. But these users are far from my sweet spot, the center of my vision. I can put less data on their representations. Of course, you have to imagine that this is viewport capture, right? So things in the corners of your viewport are not that important. You are centered in the middle. Normally, because you can move your eyes. Normally, you look at the center. Let's see how it looks like.
Mark, Joe, Isaac, Mohammed.
As you can see, when I move away from this user, it reduces the quality. You see the big points because we are sending much less points. So, from the original diagram, we can extract multiple components from the middle. We can extract transcoding. In the downlink, we could do rendering, for instance. So the device that I have, my PC, they don't have to render the final view. In the uplink, we can, let's say, move the cost of the reconstruction. I told you at the beginning, we need GPUs, machines with big GPUs. All these, especially if you want XR to be mass market, needs to get out from the user device. It's something that needs to be provided by the operators, by the cloud providers. Otherwise, the headsets will be like this. But if they are thin, you will have to buy a small box that goes with it, and we don't want this. Right. So we are in the, let's say, in the process of eliminating as many processes as possible, and we call these processes holographic, networked holographic media functions. And basically, what we are developing right now is some of these functions to render scenes, to render volumetric video on the edge, to encode on the close edge. So you send uncompressed to the nearest edge, and from there you do the compression, but not in the device, the reconstruction, and so on. And what else? Yeah, one of the things, let's say, you have many ways in a video conference, like in a holoconference, you have different ways to optimize the data that you send. But let's say that your objective is to send as less data as possible to every user, without compromising the quality of the experience. That's the objective, right? And you have different ways to do it. In the video that I showed you, the video that I showed you from 6 users around a table, we were using an MCU. An MCU basically what does is gets all the video streams, B2B or volumetric, gets all the video streams from every client, that compress the codes, all the video streams, right? And joins them together in one single volumetric video representation. And this whole volumetric video representation, when we're building it, and you know from where it's going to be watched, you can just put more points where you know the user is going to be looking at, right? That's your first approach. It's very logical, right? So I get everything, I put everything together, but when I put everything together, I only put the parts that I know are going to be watched because I know where the user is looking. Yeah, very nice, but it doesn't work. Well, it works, but only up to a certain amount of processing. Why? Because you are putting all your data, all your volumetric data in one single point, one single buffer, in one single space of memory, and this generates problems when processing and computing. So this works up to 5 users with our volumetric pipeline, and so it works well, right? After up to 5 users, you don't introduce too much delay, and you reduce the bandwidth significantly. And that's what you want. You want to reduce the bandwidth, not increase a lot the delay that you're introducing. So everything was okay. When you try with the 6th user, you start to have issues, and when you start to put more users, the thing doesn't work anymore. The thing doesn't work anymore. Why? Because you need a high-end server, and high-end server equals high costs, and we don't want this. So the approach that we are following now is a bit different, and we call it smart SFU. And a smart SFU is not very smart. An SFU means scalable forwarding unit, selective forwarding unit. But basically, a forwarding unit, what it does is that receives a video from some client and forwards this video to everyone in the call. That's probably what is happening in the system we are using right now, right? My video is pushed from my PC to a central server, and the server is forwarding my data to everyone that's watching this session. But when you start to have more people talking, that has an upper limit, right? Probably this upper limit is on the server side because there is too much bandwidth to manage, or on the client side because my client, my PC, is receiving so many streams and is decoding so many video that you have issues, right? And you know, you may be with your cell phone, so computing issues again. So you may have issues in the server, issues in the bandwidth, or issues in your client, the computing capacity. So what we are doing here is just introducing a small thing that is, I'm going to forward to you only the users that are visible in your field of view. Very simple, and it works. Because in a 2D video conference, we can see each other, right? If we're in a grid, we are 20 people, we can see the 20 faces. But in a 3D domain, the 3D domain, you cannot, of course, you can look at 100 people as a group. But if you're in a meeting, in a round table, it's impossible that you manage to see all of them at the same time, right? Because some people is not even in your field of view. This is what we are doing here. And this is working right now. The next, and this is how it looks like. See, for instance, this is a video using smart SFU with 6 volumetric user representations. Here, the reconstructions are still a bit fluffy, but if you pay attention to the number of points that we have, it's very high. So, okay, the points maybe are not in the right place, but there are a lot of points. So here we are not dealing with reconstruction. Here we are dealing with bandwidth, points, and processing. Actually, the volume shouldn't be a human body, right? But here you can see that we already managed to put 6 users and it works with a regular PC. Regular PC with GPU, you can receive it and it works. Next step for us is to get a bit farther with this strategy. So now we are not going to send only the visible data for every user, but we are going to ask to the client what type of client is, what type of capabilities, processing, networking, computing capabilities you have, and depending the coding capabilities, probably via hardware, the coding capabilities you're going to have, and we are going to transcode this volumetric video in a way that fits perfectly your capacities. So if you're connecting from a cell phone, I know that you're going to have a chipset, probably from Qualcomm, and that the video decoding capabilities that you have there are very specific. And the pixel format that you can decode this very specific. So we are going to adapt to this, right? So in the next few months, hopefully for summer, that is going to be ready. And the next video is not going to be with 6 users, it should be with 20 or 30 users at the same time. In the end, that's where we want to go. And I think this is pretty much, let me see what I have here. This is the same video, but bigger. Right. So I just want to finish with interoperability and very fast. And this is, let's say, our last problem. The last problem is the client. When you start to work in XR, normally it's because you have a PR-ready PC, and when you want to show powerful XR applications, because you have a powerful GPU in your machine. And this is a stopper for market adoption. Everyone cannot have 50, 90 in their PCs. And it's very expensive, and it's not acceptable for a mass market adoption. In the other side, the HMDs, the headsets are still bulky, right? And we want to make it smaller. But if we expect to put a lot of processing capabilities in this headset, this is not going to work. So I go back to what we were saying about the edge. We need to move some of this processing to the near edge. The near edge is going to be the cell phone, or the next edge is going to be or in your house, in your processing station, or in your telco operator infrastructure. So to get specific, the problem that we are trying to solve now is to move to represent volumetric video from a pixel format 444, right? Basically, you have all the space possible to put colors in it and to represent colors in it, and you move to a different space format where you have much less space to put colors. So you can represent less colors, less variability in your video data. And that's an issue because, as usual, if you have 40 megabits for something, but now you only have 5, you are going to lose the data, or you are going to need more time, right? So probably in the next months, again, before summer, we will be showing the same type of transmission that you have seen here in a, let's say, in a PC like the one I'm using now, that has a GPU, into something much more smaller. It's a cell phone or standalone headset. So I think this is everything from my side. Thank you for your time, and I just want to show you different events where we are going to be present, where we are going to be presenting the evolution of our work in the Presence project. All this, so next one is Laval, then the CHI conference, then the XR Expo, IBC, NEM Summit, Smart City Expo, EuroXR, United XR, and then the final review of Presence. So thank you very much for your time, and if you have any questions, please go ahead.
Hey, Sergi, thank you so much for the very detailed presentation. You really walk us through all the insights on how you build the tech. I am actually going to ask Maria, because I know it's 5 o'clock and I know people might have other commitments, But if Sergi, if you're okay and people wants to stay a little bit longer, maybe we can answer some questions. Maria, how are we? How are we with time?
Yes, if Sergi is okay, the person who
Yeah.
asked things is still in the room, so we have yes up to 4 or 5 questions. Yes, if it is possible for you, Sergi.
Yes, I go by order. Nathalie says these techniques seem to work well for static persons, seated or standing, right? What about moving persons? When you say moving, I assume that you say that they are running, right? They are running in a football field, or they're performing or something. Of course, if the person is moving in a huge area, you need a huge capture area, right? But this connects with the next question. Well, the first thing is that we are evolving our system so we can cover higher areas, higher meaning room size, right? But if you want to cover stadium size, then probably depth, time of flight sensors or depth estimation is not that way. No, just moving in the room like playing with a kid. That we can do. We will be able to do it. Our plan is to put cameras on the walls or put totems with cameras around. That should be possible. If you are not beyond the 3 meters from beyond, let's say the 2 meters from the closest camera, it's okay. But if you are beyond this 2 meters limit, you are going to have issues. Then Assistente Anonymous says, how about Gaussian splat technology? Does that apply here? Yes, it applies. There is a small or big difference. A point cloud, in the end, that's what we move. That's what we compress, point clouds. A Gaussian splat is a point cloud, but the only difference is that we use 6 parameters per point. That's R, G, B, and X, Y, Z, where the point is, what color this point has. Then we have many, many points. That's it. And we can compress this and send it to the real time. But a Gaussian splat is the same data, X, Y, Z, R, G, B, plus 27 additional parameters. So sending this data real time is still unsolved. Let's say, no one in the world is sending Gaussian splats real time, to my knowledge. But if there is someone, please tell me. Also, Gaussian splat goes very well for static scene reconstruction, right? No one in the room, you get your pictures, you reconstruct through some training, it's okay, and the result is wonderful. When you introduce some dynamics in the scene, it's not that easy. As far as I know, the latest solutions let you record like 1 minute, 2 minutes maximum, and the amount of data and storage that you need is huge. But of course, let's say in the research area, we are working in Gaussian splatting compression, trying to make it real time. But I would say we are going to need like 3 or 4 years more. And then Nathalie said, how about the protections of user data, protecting privacy or ownership of your body movement data if all the data is processed externally? Yeah, that's correct. That's an issue for every communication system. So today we don't protect, let's say we don't do anything with the data. Actually, we do not record the data, just put people and put them to communicate, and we are not recording the data themselves. Everyone you saw, they are engineers from my team. But of course, communication platforms need to be secure.
Sergi, we have another question that is similar to the last one that you've answered on the chat, and it says, what are the risks of capturing so much biometric and behavioral data, and what would make this tech safer for consumers?
As I say, if the platform owners, they are the responsibles of making these platforms safe. In our side, what we do today is we do not record the users, and we don't store the data anywhere. The data is captured, compressed, sent to the other side, and visualized and destroyed. It doesn't exist anymore. But of course, there will be potential issues, and they are going to be the same or a bit even worse than what we have in video conferencing. Right.
I have a question, if I may. Considering that getting 3D data is so complex, so scarce, right? And 3D data is kind of like the fuel for whichever AI algorithms that wants to predict things. Have you ever thought, or did you have any requests for actually storing the data or learning from the data that you're capturing, even if anonymized, for any other purpose beyond telepresence?
Yeah, we got a call some months ago from a podologist. Podolo? How is it podolo?
Oh, yeah. I don't know, but I know what it is. Yeah.
Podologist. We could.
They look after your feet, like your feet, right?
Yeah. And he wanted us. He was a doctor in Malaga, and he wanted us to put our camera system on a treadmill, so he could recording and he could understand the issues of that person walking, and they wanted to apply AI to classify the humans. So we said no, because at that time we had a lot of work, but there are plenty, of course, of applications. Another one is one of the the principal research engineer of Volume, Mike. He's working on an AI-based system to reduce the number of cameras. And to do this, we need to record some humans. Probably us, as usual, we will be recorded. But what he wants to do is to record volumetric video with 6, 7, 20 cameras, wherever, and then use only 4 of them to create the final volume. So I do the training with 30, but I only do the tests with 4.
Nice.
And we are in that process, but again, not recording the user.
Well, Sergi, thank you so much for the presentation, and I'm sure that this will be later distributed by the team, and so we can capture more audience of your brilliant presentation.
Thank you very much.
Thank you, Sergi, and thank you everyone that attended.
Thank you, Juan, for coming.
Thank you.
So bye-bye. See you then next week in the next session, right?
Yep. See you next session. Bye. Thanks.
Take care. Bye.